Today we're going to talk about neural ODEs. Um, with pins, our primary application that we used them on was PDEs. We did do an ODE demonstration kind of in this lectures here, but that was just to simplify a PDE down for purposes of demonstration. The homework we did PDEs. I wouldn't necessarily use a pin for an ODE, but they can make sense for PDEs, and more broadly, the concept of imposing equations, constraints, things like that is something that you could use more generally beyond just PDEs. So in terms of like a major theme we've seen so far, I think you want to be careful distinguishing between things that you know and things that you only think you know. Um, actually, let's start with the bottom one. If there are things that you just think you know, then you probably should not try to enforce them. So there's a lot of times maybe some uh, heuristics or some intuition built on past designs and so on that we think this is the right range of things that they should be, or this is how the design should look like. Uh, Generally, that's not a good idea to try to encode those things because we are limiting the optimizer, and the optimizer might have a better solution. We might be able to find a much better uh, solution than what we think we know. On the other hand, and this is, I think, the major theme here as we incorporate engineering with neural nets, if there are things you know, you should absolutely let the optimizer know them. Like if we know these are equations that need to be satisfied, like in the pin context, or there are uh, important constraints, or there are numerical procedures that we could use that are going to be accurate, we should definitely use them. Certainly, we could just let the optimizer figure them out through just more and more data. That's going to be way inefficient if these are actual constraints, actual invariants, actual kind of hard constraints, if you will. We should definitely impose those. And so that's going to be something you need to distinguish as the engineer. Things that are actual physics or actual, numerical relationships, invariants, symmetries, and so on. Do enforce those. Do figure out ways, and that's not going to always be maybe a canned approach how to do that. This is more of a mindset, and a pin was maybe just one case in that bigger theme. Here's an example I saw. This is a little bit simplified, but I think is a nice example of kind of that idea. It's from this paper where they were looking at electrodynamics. And in the illustration at the top, this would be maybe kind of the conventional, just vanilla neural net approach where I got some inputs and I'm going to predict this magnetic field B. Okay. And then I just run a data loss error here, right, to try to predict that magnetic field based on my known magnetic field from data. The pin approach says, well, we could augment that. Sure, let's do the data loss term, but we know that this magnetic field, for it to be physically realistic, has to be divergence free. Right? So if you don't remember your multivariable calculus very well, that's what this expression here says. This should be zero, and so they're just going to add this here as a loss term and weight it. Right? This is what we call a soft constraint. So we could do better. And for some reasons, we talked about some. I didn't go in super depth, but as an optimization person, we would rarely use soft constraints in the field of optimization. I mean, there are cases for it, but we would try to avoid them, and certainly we would use a constraint optimizer when we can, and that's certainly an option. But there are other times when you could maybe encode some of these relationships. So in this case, we could, for example, have a neural net that learns this, we'll call this A, and we'll then construct B by taking the curl here of A. And from multivariable calculus, you might remember, or might not, that if we construct this vector field from the curl of A, it's automatically divergence free. In other words, the divergence of this term, of a curl of anything, no matter what this is always zero. So this term is automatically satisfied by construction. So we no longer need that as a constraint. So here we can still satisfy or drive things based on data. We are immediately, or always, I should say, generating candidate magnetic fields here that satisfy the physics, at least in terms of its divergence-free property. And so that's, again, this is not like a canned thing that you're probably going to just apply. You're probably not going to do the same. but a broader theme here of can you incorporate constraints made by construction? And you might also think about using actual constraint optimizers, a little more advanced, especially with batching. That's an area that's needs development. But if you can do full data batching, certainly you could use the techniques that we use, like in an optimization, to do a constraint optimization. But yeah, this is powerful, imposing things by, and there are a lot of papers that you see a lot of different techniques to do these for different problems, but often it's going to be in an engineering context, kind of customized to your problem. All right, let's get to neural ODEs. And you might think about what's a theme here as we look at neural ODEs. There's certainly some shared themes here, but I think some new ideas here in terms of themes to think broader beyond just the neural OD problem. So I'm going to motivate this from an engineering perspective. This is not how it was actually originally described or proposed, if you will, in the paper. I'll also show that kind of motivation as well. That's maybe more of a computer science perspective, but I'll take it from an engineering perspective where we are thinking about differential equations from the beginning. Quick review, hopefully you remember your ODEs, but in an ODE we define, and this is written in this generic form, where I have some function of my independent variable, which I've written t, it doesn't have to be time, but that's a very common one, any independent variable. And then I have my dependent variables y, which is in general a vector, right? So I can have many states, and I need to define this function that outputs the derivatives of all my states with respect to this input independent variable. So again, if you remember from ODEs, I can have higher order differential equations, that's fine. And I can convert those to sets of first order ODEs as long as I can isolate my highest derivative. I can always do that conversions, again, as long as I can isolate that highest derivative to a set of first order ODEs. So this is very common, this kind of general form where, again, y could be a state. It's a vector. So it could be like a position and a velocity, and the derivatives would be a velocity and an acceleration, for example, and that would be used to maybe predict a trajectory. We call them trajectories in general, whether it's position or not. But yeah. So my goal here is to predict y. We also need an initial condition. We could do also boundary conditions, like a boundary value problem. Here I'm going to write it in terms of initial value problem. So you've got initial, this is the most common, initial independent variable time here. We'll call it time, even though it doesn't have to be time in that initial value. We know what the solution looks like, so to speak. Y is going to be my initial point plus this integral. But the problem is this integration is challenging because f depends on y, right? So the solution, the thing I'm trying to solve for, depends on itself. So this is not where we can use like a simple integration techniques like a trapezoidal or Simpson's rule. We need better approaches, right? And this is where you've seen the simplest being Euler's method, and maybe more popular methods commonly used are Runge-Kutta, fourth order, usually adaptive fourth, fifth order methods are what are commonly used. But there are a whole family of them, tons of them that I'm sure you've seen. And so what we get is a trajectory, this y of t, this is what we're trying to predict. We have an initial condition, y0 at t0. We could plug that in and get this initial slope, if you will, or direction. And we're trying to do this integration with our ODE solver to solve for y of t. And here I'm just showing one state y, but in general, I can have many states. Okay, so that's just a quick recap. As an image, in terms of this process, we might think of, okay, I always define this ODE function. It takes in y and t as we just described, and it outputs dy dt. And that's, when you've used ODE solvers in the past, you always write it in this generic form. You write this function y of t, and it outputs dy of dt, and you give that function handle and your initial condition to the ODE solver, right? And it can run with that. If you don't remember the details of RK45, and that doesn't really matter because that's going to be your default in most ODE solvers. It's going to run with that, right? You give it the initial condition, you give it this function handle, and it's going to integrate that forward in time and output this trajectory. Okay, so that's kind of the picture. And now let's think about what we could do in terms of incorporating neural nets. Well, a first approach we might do is to say, Okay, I might want to be able to replace that entire thing with the neural network. This would be what I call the naive approach here, a simple approach here, meaning I could train this by giving it initial conditions and trajectories. I can collect a whole bunch of data based on different initial conditions and their corresponding trajectories, and then I could learn that process. And I could certainly do that. That certainly is something that we could do. But perhaps a better approach is if we go back and I don't know what's happening with my thing here. I can't seem to go backwards. Okay, here we go. If I go back and look at this function here, instead of replacing the whole thing, I might say, well, you know what? I actually know I have really good OD solvers already, right? Like these are things that we've studied for decades, and we know we can prove things about their convergence and their stability, and there's a lot we could say about them, and we know a lot about the behavior, and we have a lot of options for ones that ODs that are stiff and non-stiff, and we have adaptive solvers. Like I would really love to use that. And that's not the thing that I don't know so well. So you're thinking about that theme about what do I know, what do I not know? I know how to solve ODEs pretty well if you give me that ODE function. And so there might be cases where what I don't know very well is that ODE function. So let's replace that. But let's not replace the whole thing, because if you could just replace just that ODE function with a neural net, I can do that time integration no problem. I mean, that's the part I already know how to do really well, like no matter what it is. So that motivates this kind of architecture here where we say, let's not replace the whole thing, just replace that physics portion, if you will, or replace that portion of the problem that says, what is dy dt given y of t? If you can give me that, like I didn't really care how it came from, it could come from neural net or equations. Either way, if I give it to an OD solver, it can run with that no problem and output a nice trajectory, into some desired tolerance and so on, and adaptively and efficiently, and it's great. So that motivates this approach, which we'd call, well, this is in essence what the neural ODE looks like. And so you might be asking yourself, okay, well, how is this better than just replacing the whole thing with a neural net? Well, in part, it makes it much easier for the neural net because I have reduced its burden of things it needs to learn. If I have this approach, I've got to learn the whole thing. I've got to learn not only this relationship of how things transfer between y and dy dt, but I've also got to learn how to do ODE integration, right? I mean, that's not exactly how it's thinking of things inside the neural net, but effectively, those are the types of things I'm having to learn. Whereas in this approach, all I have to learn is just how to do this for any given time step. Like I don't need to figure out integration forward in time. I just need to learn if I'm given the states, what are their derivatives look like, at any given time step. So all I have to do is learn that function. That reduces the burden, the complexity of the function I need to learn a lot. And so I will not need as much data in general, right? So that's going to be better. That probably means, or for a given amount of data, I'm going to be most likely much more accurate in my predictions. Okay. So then you might ask, well, why would I use a neural net here? Why wouldn't I just encode some equations? And certainly you would. If I knew the equations, again, if they're things I know, I should use them. But we'll do cases where I may not know those equations, or I may not know them very well. In the homework problem, we're going to do something related to weather prediction, and that you can I think easily convince yourself of the case where, that box, I maybe have some physical relationships, but it's kind of fuzzy. It's not so easy to predict, the differential equation corresponding to the weather. But if I could maybe learn that from data, I could then integrate that forward using any conventional ODE solvers. And certainly it does not need to be an all or nothing, as we've discussed. Like I could use approaches where I encode some things I know maybe some equations or some portions of the equation, and maybe they're just the coefficients and things I need to learn there, not the whole thing. But, broadly speaking, it could be I just learned the whole thing. Right? I really don't know. I don't have any equations for this perhaps, and I just have data. But I'm not going to try to learn the trajectory. I'm just going to learn from these individual data points in trajectories, like what's the differential relationship. Okay, so that is basically the neural OD in this in a nutshell. I have now a little bit of a different loss function. I mean, actually, it's really going to be quite similar. It's going to probably use a mean squared error here in predicting my trajectory against some known trajectories. But the difficulty here, I guess we want to point out, is that the loss now depends on this integration, this ODE integration. So that's actually in the loop, if you will, of back propagation. I need to figure out how, as I'm propagating, well, yeah, I guess I'll say it this way. Even though I have the neural net only learning this one piece, I'm actually wanting to compare against full trajectories, right, to make sure this actually works. So I'm considering this as a system, if you will, which again is another broad strategy here in kind of these physics learnings that I'm combining traditional layers. As we'll see, you don't have to think of a layer just as this kind of linear thing, an activation function. That's all we've used so far. I mean, I gave you that magnetic field example. Well, what's the curl? Is that a layer? I mean, you could think of it as a layer. It doesn't really matter. I mean, I can do any sort of calculations I want in between. I could have layers and any sort of arbitrary calculation. It does not have to be kind of these conventional off-the-shelf type of layers. Anyway, so here we are. I've got this OD solver. It's all part of my learning process. And so I need to do back propagation through this whole thing. And that becomes more difficult, right? It's not just through just the neural net portion. And there are two ways that this is done or could be done. We call this discrete or a continuous unsteady adjoint. I'm not going to really get into the details here. I linked some links in the reading. Of kind of my derivations of how this could work if you're interested in more detail. But in brief, these are two approaches to do the derivative computation, and an adjoint is analogous to kind of this reverse AD or back prop as we've been talking about. In the discrete sense, it is effectively, I mean, it is exactly in the explicit OD case, it's exactly just reverse mode AD. Or back prop, but there's some things we need to do to make that efficient. So if you think about the OD problem, what's happened? Let's just do Euler's method to be simple here. I got initial condition. I've got this function that's this neural net that tells me f, or which is dy dt. And so I take my initial point, I evaluate dy dt, and I multiply by some delta t. That takes me to a new step, and I evaluate the neural net again. That gives me that dy dt, and multiply by dt, and I keep moving forward, right? In Euler's method. All of that is just, multiplications and additions, and then evaluating a neural net, which has its own, multiplication, addition, blah, blah, all the linear layers and so on. So that's not hard to do back prop through, right? It's just a bunch of mathematical operations that we could do already. And so I just need to make sure I have, rules, as we call them, defined for all those things so that the derivative can backwards propagate through that. And again, like I said, there are some details to do this in memory efficient ways as we do larger problems, but in essence, that's relatively straightforward. In the continuous case, it turns out if I'm clever about it, I can rearrange the equations and show that I can get those derivatives by solving a set of ODEs where I integrate backwards. It's not the same set of ODEs; they're a related set, but different set of ODEs that I can integrate backwards by doing another ODE solve. So I do an ODE solve forward to get my losses and so on, and then I can do an ODE solve backwards to get my derivatives, and that's the continuous. It's called the continuous. Of course, I have to discretize anyway to do the integration, but we call it continuous because we can write it as an integral. Both these options will be available when we start using these next time in code. As a broad, and again, your mileage will vary as for different problems, but in general, I would say discrete tends to be more accurate and continuous tends to be faster. Again, it's a little bit of a broad generalization. It won't be true every time. We have a long history of discrete and continuous adjoints in the optimization world. And I think the same battle's playing around here in the unsteady world, but coming to the similar conclusion where in the early days, everyone thought continuous adjoints would be the best because they're mathematically elegant and consistent with the math. But in practice, discrete adjoints just work much better. They're just, and that's because they're consistent with the actual implementation. The actual computational implementation is discrete, and the discrete adjoint is consistent with that. And so those derivatives are numerically consistent, and so they just work much better. In the unsteady case, I think similar stories playing out. Again, not always, right? There are exceptions where the continuous will be better, but where I think there was a lot of interest in the continuous unsteady adjoint. It's mathematically elegant. And there are cases where it's nice because you do have an option here to use actually a totally different ODE solver for the backwards case if you want. So there's some niceties there. But again, the discrete one is consistent with the implementation. So I think it does tend to be more accurate. That's not always what you want though, because continuous, like I said, actually tends to be faster in a lot of times. So in the engineering problem, sometimes we need that higher precision, right? We've talked about needing double precision, things like that sometimes. So it's something you can play with. I think for the homework problems we're doing, either one will work just fine. And so often you'll want the continuous just because it'll be faster, but just throwing that out there. Okay, now I want to go through maybe the original kind of motivation for this problem, and partly to show it, but there are some concepts here that are broadly useful for us in engineering. I think we less often use this idea of a residual net directly. I had a slide here. I must have lost it. Let me see if I can add that back in, if I can find my mouse. I'll pause it real quick. All right, found my slide. So this is from this paper called Residual Neural Networks. Or sorry, that's not what it's called. It's called Deep Residual Learning for Image Recognition, but this approach has been called a residual network. And what they were finding is that they were creating these networks that were, reasonably deep, 20 layers. And as they would go deeper, that's a 56 layer case here, the training errors and test errors would be worse. And in principle, they should be better, right? As you add more layers, I've got more complexity, if you will. I've got more, I've got more possibilities. I've got a richer function space that I'm searching over. And so in principle, I should be able to do better. But for reasons that we discussed before, going deeper would lead to issues, particularly with vanishing and exploding gradients is one of the issues that we see that we talked about. And so in practice, it was not training better. And so they proposed this idea of a residual network. And the idea here on the left is that imagine I've got some input X and I got a layer, an activation layer, and blah, blah, and I only drew two, but imagine there's tons of them. Okay, but two is fine. And so at the end of that, we could just call that thing H of X. I mean, that's just an arbitrary name, just meant to describe that I went from some input, and this does not have to be the input to my neural net, it's just the input to that layer. I'm just thinking of some subset of layers, and there was some sort of function happening here with layers and activations, and I get to H. Okay, on the right is an illustration of a little modification we can make. This arrow on the right, we call this a skip connection. And the idea is I still want to get to H by the time I'm on the other side of these steps, but I'm going to call what comes out of my layers out of this process here. I'll just call that F, and I'm going to add it directly to whatever I had before I went through these layers, right? So that's X. So here, H of X is now the sum of F and X. So all I did, and this is why it's called a residual, is instead of trying to learn H directly, I'm trying to learn the difference between H and what I already have, which is X here, right? So if you look at that equation, if I said H minus X, that's F, right? So that's a residual, means the difference here. I'm trying to learn the difference between where I'm at, X, and H, right? And again, this need not be the input to the neural net and the output to the neural net. It's just could be some intermediate section here. And this is a broad theme that's useful in engineering where you can often, not always, but you can often do better learning a residual rather than trying to learn a function directly. This is used a lot in multivariable physics type things where, let's say I've got this fluid simulation and I have this high fidelity fluid simulation that's awesome and it's super accurate, but it's expensive. And perhaps I have this low fidelity simulation that's really fast. It's not as accurate, but it's pretty reasonable. And instead of trying to learn that high fidelity solution directly, I could learn the difference between the high and low fidelity. So I could run the low fidelity and then add that correction to it. And often that'll be a much easier function to learn. That's kind of the similar intuition here, right? Is if X is a reasonable thing, I could learn the difference between them much more accurately. I mean, that's one way you can think of it. That's maybe not the traditional way. Um, and I'd say in the physics context, that's been done a lot, not just with neural nets, but with optimization in general and surrogate models, kind of this multi-fidelity surrogate. That can work well. It can also work poorly if your low fidelity is a bad prediction of the high fidelity, right? Because then the thing I've got to learn is perhaps more complicated because I learned this difference that's actually more, like a really bad approximation. But in general, if you have a reasonable approximation, that difference can be a much easier function, right? The difference between those two functions can be a much easier. Anyway, in the more neural net context, maybe a more traditional motivation here is that this will help with the backprop. So that exploding or vanishing gradient problem is relieved by quite a bit because instead of passing through, I do still have to pass through tons of these layers, but I've got this other path that goes around. So that gradient signal is preserved like directly there because all I'm doing is going from X to X. So a portion of that, some information is just going to be passed all the way back without any issues whatsoever. So I can avoid a lot of that headache there. So anyway, all that is kind of this idea of a residual net. You may or may not, that's maybe less often that we use the residual net in engineering directly, but the idea of a skip connection, very useful. And this idea of residual learning, I think, is also very useful. Okay, but then from that, these authors of this paper, which I'll show you in a second, they looked at that equation there and thought, hey, that looks a lot like Euler's method. They were not approaching this as a way to solve ODEs. In fact, ODEs was not really in their domain, and had to go relearn. Like, oh yeah, I've seen ODEs, but it's not. They're not thinking about solving ODEs. They're thinking about, hey, look at this problem here. That looks a lot like Euler's method. So I wrote here at the bottom. That's what Euler's method would use, right? Where I guess I've absorbed the time step, if you will, but um, it's analogous to that and said, well, what if we could, instead of using Euler's method, let's use something better, or think of this as a continuous ODE that we're trying to solve. And so that's a cool idea, right? And this is, I think, I keep using the word theme today, but this is a theme from, I think, innovation. A lot of times when you see impactful innovations, it comes from taking things from different fields and seeing a connection and bringing things over. So just a plug to maybe look a little more broadly than your current domain, find more innovative solutions and try to bring ideas across in different ways. So anyway, that was their motivation. And here's kind of a picture from that and a reference to the paper. I've also linked that in our reading today. So in the traditional residual network, the analogy is like, well, it's kind of like doing an Euler's method. It's a little bit coarse, but maybe we could think of this residual network as an ODE, a continuous ODE problem, and they'll use a continuous adjoint in this case. Again, of course, you have to actually discretize and practice, but now you can perhaps get much more accurate, much richer solutions here. Yeah, and I should say on a reading, I provide a lot of readings. I don't expect you to read all of them in detail. They're meant to be references. Some topics should be merged in others, and so you'll want to read in detail. Others, it's enough just to kind of skim through and get a feel for some of the main ideas. So that's the derivation or motivation from the traditional computer science side. Is it's a richer version of a residual network, more continuous version, if you will. For our case, I think it's from the engineering perspective, it's more natural to think of it in terms of an actual ODE that we're actually trying to solve ODEs, right? And we want to replace just that portion where we predict derivatives with a neural network. So that's an overview. Next time we'll get into some code. We're going to use a package, PyTorch StiffyQ, and we'll start playing with that a little bit and see how we could solve some of these problems.